We're now going to move on to the first of our demonstration sessions, which will be chaired by Professor Carsten Maple. And then we will have a number of presentations, including from our demonstrations from my colleague Yang here at Surrey. So I'd like to hand over to you, Carsten. Hopefully I can hand over to you.
Thank you very much,
Yes.
Martin. Thank you. And thank you to Dan, Richard and Sue for a really interesting panel discussion then. As Martin mentioned, what we're going to do now is talk about some of the demonstrations. There's been a lot of work over 5 years undertaken within the Fair Space Hub by each of the universities. And a year ago, we set out with an objective of bringing together some of those innovations that we've done, some of that leading research, to bring something practical that could be of use. We're going to show 2 demonstrations today, and I've got to thank Dan, Richard, Sue, and all of the international and national members of the advisory board and steering committee for helping us in shaping these demonstrations. These demonstrations bring together work in the first demonstration from Surrey, Warwick, and Salford. That's what you'll see. And in the second demonstration, we'll see work from Salford, Imperial, Edinburgh, and Warwick. But there's much more work gone on behind the scenes. I'd really like to thank both Alex over in Edinburgh, who will introduce the second of the demonstrations, and Yang, who I'm going to hand over to now, who will do an introduction and tell us about the first demonstration that brings together the technologies, and that's on active debris removal. So Yang, hopefully you're there in Surrey, and I can hand over to you.
I am, Carsten. Thank you so much for the introduction. Good morning, everybody. It's a pleasure to be here and talk to you about the essence of the first demonstration of today on active debris removal. I think that connects extremely well with what Dan has been talking about in the panel discussion. You know, this being a highlight of immediately available mission opportunities for what collectively we did in R&D from the Fair Space Hub. So if I can have my slide up on the screen so people can see it. Just give us a second. I think our technical team is working on it. Okay. All right. Can we have it bigger for the audience in the room? Excellent. Thank you. All right. So just a few more words about the background of the ADR mission. So it's very widely recognized by the United Nations, G7, and the latest UK published National Space Strategy that space debris is a key priority for future sustainable use of the space. And also just for the audience to be aware, the spanned rocket stage is actually contributing to the 18% of the space debris right now. And for instance, we take a quote from the Space News, who announced that the upper stage topped the list of the most dangerous space debris. So capturing, removing this orbital debris, also known as non-corporate targets, using robotic manipulators is actually very useful means because it's introduce less risk to produce and generate smaller debris compared to more intrusive methods. So robotic arms enables control of all the phases of that operation. So pre-capture, impact, meaning engagement, and as well as post-capture. So in fact, we went through a very rigorous review process over the Fair Space project. So we've been through critical design review, which took place over 12 months ago, where we get recommendations to choose the ADR as one of the final demonstration during the showcase. So the concept of the demo, just to give you a top-level flavor, which we're using the span apogee kick motor as a target. So in the real world, it looks like what's in that picture in the right circle there. So we're going to use that as a target during the demonstration of the robotic capturing and removal. And this is quite important for us to demonstrate some of the key research novelties that address the key technical challenges that currently are the gaps in the industry, in the state of the art. So on this slide here, that broken down into 3 areas: the visual navigation with non-cooperative targets. Of course, as we know, in the space environment, there are a lot of challenges for the camera to work because of the very lighting conditions. Some of the surfaces have reflections due to a strong light source and metallic surface properties. So it's very stressful for the computer vision, machine vision to work autonomously at an accuracy that we desire. There are a lot of disturbances as well, uncertainties. Obviously, we can't fully and accurately model beforehand. So we have to deal with on the flight. There are also challenges on the guidance and control for the robotic manipulators and effectors. They reflect high degree of freedom systems. So it's no trivial to get its work. You have to avoid collision. You have to make sure the control is optimized so that you can make sure it works with the limited onboard processors that we have even in modern spacecraft. Of course, that last bit, that docking bit, that grasping bit is very challenging, both from the hardware perspective as well as the software. Okay, you have to have the visual guidance for that grasping. You have to smart about where to grasp and make sure it's secure, because there could be security issues involved. And also post-grasping, you need to make sure the new integrated system post-grasping is also stable and secure. So that's the range of technical challenges we have addressed in our demo. And just to give you some reassurance, and this is with close engagement, consultation with industry. For example, one of the leading players in the space sector, GMV, they pioneer spacecraft agency and capture technology for ADR missions and services. And we receive a call from Mark, their CEO of the GMV UK branch. And he said very clearly, the research that conducted by our team is vital in developing novel concepts as well as supporting space industry to mature the solution, guarantee that this innovative solutions are available to meet the demanding needs. I think what is also brilliant for Mark to comment that he recognized academic development has to be coupled with industry involvement and investment to secure success of this future services and also sustainable and fair use of space for all. This is a picture, a kind of, preview of what you're going to see in the actual live demo, because I can then explain to you what it entails. So it is a 2 robotic arm system. On the left of this image, you're seeing the arm that represent the servicing arms sitting on the spacecraft or potentially space station, and it carries and effectors. And on the left-hand side of the picture, you're saying a robotic arm carrying the potential target objects in space. And we need that arm to simulate orbital dynamics of that object in space so that we can very well represent its behaviors. And the setup is in a laboratory environment because then we can introduce the lighting conditions to mimic what is happening, all these challenges in space, but at the same time we can calibrate, we can know exactly what they represent through our ground truthing system. So we can repeat the experiment, we can be very sure what exactly is happening with the solution we produced, calibrate them and knowing exactly what we think is happening in the robots. So to give you some further ideas about why this setup is actually very useful, for instance, we can make an effector on the servicing arm with different type of solutions and technologies. For example, here in this demo, we're using a commercially ready two-fingered gripper, which represent the minimalistic mechanism capabilities on the arm, which we think is commercially, close to the, readiness level we need for real-world missions, and we enhanced it so that it can address some of the gaps it currently, doesn't have in industry. And we also can have brand new design of the robotic gripper, for example, produce one of our team members. And we could also have other kinds of and effectors with, for example, to do with corporate target, which you can have a predefined mechatronic solution. Similarly with sensors, for navigation, it has to be visual guided because of the sophistication of this challenge. So that also has a range of RGBD type or pure LiDAR or pure stereo camera or high-res cameras. And on the target side, so we can have the AKM, obviously we've seen that in the live demo, and also CubeSats, for example, they also can be potential object as a space-day bridge. And similarly, you could have the other side of the connectors if this is a corporate target, just to give you an idea how diverse and versatile this testbed is. So when it comes to the demonstration itself, just to give you an idea what is the mission phase we're actually trying to replicate and demonstrate here. So this is the docking phase, which is really the most critical proximity phase of the mission of the ADR. Obviously, this has to be post the rendezvous phase. So you can see these key building blocks lined up on the slide. And then on the bottom side of the slides, those modules correspond to those mission modules that is contributed by our testbed. Okay, so it's all relating to what the real mission is involved and needed. And then further from there, I highlighted 4 boxes on the top that actually summarize the key underlying research that delivers that list of novelties and challenges we addressed, okay, in the actual demo. So for instance, the top 2 are coming from Surrey. So one is a software-driven research output, which is a visual guided solution, which can do the job at a very cost-effective and optimized way. And there is also hardware contribution, which we enhanced and enabled a commercially existing 2-finger gripper to work in this case. And then the other 2 further boxes, one is from our colleagues in Warwick that look at the software enhancement to improve the security measures for the navigation algorithm. And then contributions from Salford, which is a new development of the two-finger gripper that hopefully is on the way of solving this problem better. So just give you a few more words about the actual technological advancement and their TRL levels. So I talk about the visual navigation. So as you can appreciate from the pictures on the left top, you can look at you can appreciate the homogeneity sometimes in the spacing. You can look at sometimes how featureless that object can be in front of cameras. Even if you put a pair of human eyes there, it will be challenging, to navigate accurately with that sort of spacing. So we come up with this solution, which has a AI-enabled capability, meaning in the backbone, we have deep learning. Okay, so this is ranked top 3 worldwide in the ESA Grand Challenge. So at least, we know where we compare to the international players in this area. And you will see the actual demo of how this actually works. And then similarly, on the grasping side, as being said earlier, if our technical team can help me play that, thank you very much. So you can appreciate how the visual guided control for the gripper is very critical through this animated film, but of course you will see the real thing a bit later. And this is extremely important for us to guarantee that this operation will take into consideration of what's mission critical, such as a minimalistic force and equal balance, so that the whole grasping and post-grasping would be very stable. Just to highlight how serious we take the commercialization and industry collaboration through this process, just to echo some of the panelists have highlighted. So for instance, we through this work, we have a spin-out company itself. So one of my colleagues, Ian James, is actually our business development manager on board this business. And there are other UK-based business we'll be engaging through this whole process. And these are a few key highlights on the hardware enhancement on the gripper itself that took place in the past 12 months. I have our researchers that will give you further details during the live demo. If I can have the film playing, the first one, so you can appreciate that on the left-hand side, that's before the actual hardware enhancement. Of course, the visual guided navigation works all brilliantly, as you can see playing there, until the retrieval bit, and you can see how inadequate that commercially ready gripper is in that stage. So with our enhanced system, where you can see the overall system view and also the close-up view from the robotic camera itself, and you can see how the rigidization post grasping is still successful. So you can appreciate what magic this is making. And similarly, I'm going to go through at the top level, the novelties our Salford team have contributed in terms of developing a brand new dexterous gripper. Again, we limit the number of grippers to 2, so that there's a reduction of the unnecessary cost there. And there's also something very smart about the control, which is flexible and adaptive, so that it can deal with that sort of challenge with rigidization, as I was highlighting earlier. So here, just a few further words of things that has been done, particularly in the past 12 months of the research program, and particularly the optical sensor enables sleep detection is an autonomous way of addressing this kind of common problems. And particularly, as you can see by the image on the left top side, the gripper sometimes has to deal with not just the nozzle of the upper stage, but potentially CubeSat system, which has a squared edge that has to deal with this kind of very polished surface. And moving on to the Warwick's bit, which as mentioned earlier, this really looking at how to improve the security measures for this such a critical activity in the ADR process. So we have, so they help to identify the attack tree for the ADR mission. So there are a list of them, but of course, for the sake of the ADR demo itself, we have to prioritize one of this attack from that list. So the ones we pick up is in relation to the sensing, because that can be quite easily attacked, and also the damaging impact of that is most severe. So that's the reason why we choose that as an example to demonstrate their data-driven approach to verify the integrity of the sensor input to the GNC system. So this is just based on, for example, give you some flavor of what you might be saying in the real world demo later on. So for example, the picture on the left are giving you examples of tamper data which involve point clouds, and how the algorithm on security can help rectify that or pick up the risk, by looking at a 2D RGB image, which is coming from the servicing spacecraft itself. So that would, I think, give me ample time to actually hand over to my colleague, Sam, to kick off the real world demo. So Sam, are you online? So Sam actually is physically located in our lab, which is across the road from this building. Here you go.
Good morning, everybody. Hi, Yang. Yeah, I can hear you.
Excellent. So over to you.
Thank you very much. Thanks for the detailed explanation. Hi, everybody. My name is Sam Simai. I'm a postdoc researcher in the University of Surrey. Professor Yang already emphasized high-level details about these experiments and this mission. I just briefly go through a few technical details and challenges that we faced for this specific demo and specific test. And then I gotta show you how the system works. What we have here is a full autonomous system. I just wanted to emphasize that. Full autonomous robotic grasping system. Our experiments consist of two major blocks. You see the, I'll call it right robot. That's the first part, that we have got a Star 24C nozzle, rocket nozzle stage that attached to a UR5 robotic arm. And that works on the free drive mode. I come back to this when I briefly talk about the challenges that we faced in this experiment. And on the left side, we have got our robotic arm, depth camera, and lots of other sensors that are attached to another UR5 arm. And basically that mimics our service vessel. Okay, so in this part, basically our RGBD camera creates the point cloud and generates some grasping point on the nozzle. And you should be able to see the point cloud actually in a live mode. You probably see me on the side as well. We have got several algorithms that work at the same time and creates a trajectory required for that our service robot to come and grasp the rocket nozzle and deorbit it, basically. All system has been developed in robotic operating system, ROS, and basically it's, as I emphasized before, it's a fully autonomous system. So let's go to challenges. As I mentioned before, it's a real difficult job to mimic the microgravity on the surface of the planet Earth, because we cannot basically have all the motions and things that we have in a real environment, in the orbital environment. We cannot actually create all of them here. It's going to be real difficult. But the solution that we came up before was having a robotic arm on a free drive mode. One of the problems that we had with that solution came with the fact that most of the robotic arm have got safety features that lock themselves automatically. So to tackle that problem, we create a physical switch and we override the software system to basically actually create some smooth movement on the robotic arm, basically on this one. So our right robotic arm is not attached to our ROS system, and it actually just moves freely to anywhere that we want. The second challenge was the grasping point, actually. So as you see, that rocket nozzle looks very homogeneous, basically. It has got a symmetry plane in middle of it, but the cross section of it that we want to do the grasping has got a very complex shape. On one side, we have got a parabolic shape that descending towards the center of that conic area. And on the other side, perpendicular to that surface, we have got a piece of the arc of the circle. So none of the off-the-shelf grippers could basically hold the rocket nozzle in a way that we wanted to do it. So the solution that we came up was designing a new gripper system, fingertips, the enhanced one. Okay, I tried to do that, show it here to you. So I'm hoping you would be able to see the details here. So that new fingertip has got, we have got a maximized surface area to create a better touch with the rocket. Same time, we use anti-slippery material for grasping. Basically, actually, it increased the coefficient of the touch to the nozzle, and also the combined compressibility and some 11.5 degree of flexibility on each side of these gripper tips. So this new design actually is flexible enough to match the shape of the rocket nozzle and grasp it most of the time. So the success rate that we had before this new gripper tip was something around 60–65%. Now we have something over 95% of success rate of the grasping. So I think I explained everything, basically. I don't hold you any longer. Let's show how the system works. So that's the first test. So now we run it one more time. And as I said, it automatically actually generates some random points. Hopefully it's going to go for another grasping point. You can see on top right corner how the grouper actually, how flexible is it and how it shapes to match the shape of the rocket nozzle. So perfect, we have got 200% success here, and that's our lucky day today, I think. Thanks for your attention. It's time now to see our work of our colleague in University of Warwick regarding to cybersecurity of robotic grasping. Thank you. Thanks, everybody.
Thank you. So can we shift to, okay, we will move to the second of the three demo. I think our colleague Saurav from Warwick, I think he's today based at Imperial site. Saurav, can you hear us? Excellent. Yeah, I think we have your video on. So over to you, Saurav, if you can hear. I think we're just trying to connecting audioly with our colleague. I think Saurav is actually, he's based on the Imperial side. Carsten, just wonder, Carsten.
This is the first one with no attack.
Oh, hi, Saurav. Yes, we're connected. Over to you.
See the normal operation of the grasping algorithm. And in the inset, you can see two images.
Could you restart
the on the left is the original data, and the right image is the modified data. However, as there is no attack in this scenario, the left and the right images are exactly the same. As you can see, in this case, the robotic arm has no trouble finding the target, grasping it, and then pulling it towards itself.
And as you can see, so can you play the next one, please? The one with the cyber attack.
In this part of the demo, we showcase cyber attacks and cyber defense for the ADR system. We have three different scenarios, and this is the first one with no attack and no defense. In this setup, you will see the normal operation of the grasping algorithm. And in the inset, you can see two images. The image on the left is the original data, and the right image is the modified data. However, as there is no attack in this scenario, the left and the right images are exactly the same. As you can see, in this case, the robotic arm has no trouble finding the target, grasping it, and then pulling it towards itself.
So this is the first one with the normal operation. Can we move to the second video, please?
Scenario showcasing the attack. In this case, the attacker gains access to the point cloud data and moves the data point to the right. You can see the modified data on the right image in the inset. As the grasping system relies on the integrity of the sensor, it calculates its grasping point based on the modified data or the adversarial input and follows the wrong path and tries to collect the debris at the wrong location. So the robotic arm fails to grasp the target and the mission is failed. The system can make several attempts to grasp the target. However, all of those will fail because the point cloud data is modified by the attacker.
cyber attack. So this third one will showcase the defense.
The third scenario showcases the cyber defense mechanism. In this setup, we utilize the RGB camera that is mounted alongside the IR cameras generating the point cloud. The point cloud data is once again modified by the attacker and moved to the right. However, in this scenario, we use the RGB image data and compare it with the point cloud data. Then by comparing the two modalities, we can approximate the location of the target once again, and then use our grasping algorithm to find the correct grasping point. You can see the corrected point cloud data in the bottom right image of the inset. As you can see, the corrected point cloud data may not be exactly as same as the original data, but in this case allows us to find the approximate target location and the mission is successful.
Thank you. That's the end of the video. Thank you. So we'll move to the Solforce demo.
Thank you, Sam. Thank you, Saraf. Appreciate that. Okay, great. So,
Here, we introduce a dexterous two-finger gripper integrated on the ADR demonstrator setup at the University of Surrey. This experiment demonstrates a robust and a stable grasping of a CubeSat, which is otherwise not possible using a commercially available end effector. This gripper allows the service vehicle to pick a random contact point on the object and adjust gripping orientation locally, which in turn improves the vehicle's overall energy efficiency. The proposed sliding mode controller, combined with the optic sensors providing qualitative feedback, facilitates a robust and redundant slip detection and avoidance for the gripper. Dexterity and agility of the gripper is further challenged by performing a stable grasping of Surrey's mock-up nozzle. As observed in the gripper view, the thin edge of the nozzle is effortlessly grasped by the lower joints rather than the tips, proving the effectiveness of the redundant grasping control.
overseas, so I appreciate the effort of making that narration file, and so that people can see how the brand new also research development can also help us demonstrate the capability. So that will take me to the Q&A part of the first demonstration in the morning. So we have I'm sure our research teams are now spread out in different physical locations, but we're all here to answer any questions regarding the demo or the research behind the demo. And of course, bearing in mind in the afternoon, as Martin already introduced earlier, that in the afternoon we do have dedicated research talks by the academic investigators, and that would be another opportunity in the afternoon to look into some of these key texts. So I could invite yes, we have a hand raised just for everybody spread different size. We have a question from the floor on the Surrey side. Yes, please.
Hello,
sir.
my name's Mike Rustow from Brunel University, and this was really fascinating, actually, all of it. I'm a structural engineer by training, got some background in AI, so this is really interesting to see what the human race is doing in terms of, you know, extraplanetary exploration and all of this sort of stuff. Now I can see that the space debris removal is clearly very important, and you know, if we don't clear that, then we could essentially have this belt of small pieces that prohibit any further exploration. And the demonstrations you gave were fascinating as well. And I'm just wondering, is there some proportion of debris that is in rotational orbit as well? And whether that's something you plan to look at in the future, or whether it's just there's such a small number of that you just say, look, that's too small, and there's, you know, it's a very, very technically challenging aspect. Because the thing which you were catching onto there was obviously aligned with the robotic arm. You know, you might
just to clarify, when you say the rotational behavior, do you mean it has its own rotational orbits? Yeah, so say it's rotating on its own axis whilst it's inertial space. That's right. Got you. Yes, indeed. As you can see from the demo we explained, so we have to go through a rendezvous phase. So we have to remove some of the relative orbital movement between your servicing arm and the target first before you perform which we call relative navigation stage for the, you know, proximity GNC and docking. So that's a standard space mission process. But when it comes to self-orbiting rotational behavior for the object, I think there are various ways we can address it. First of all, you can try to remove that relative orbital motions first, as much as you can, okay? And then you would need to look at where and when to grasp, even though it might have a rotational behaviors in itself. That's why in one of the few kind of video you've seen, we have to move the robotic manipulator or gripper around. I think you can appreciate, you know, when you have to move around that target object, when the inertial behaviors is complicated, you can't remove all the relative rotational motions, so you have to move around. But the inspection or the mapping of the object, it still stands. You basically have to determine where are the right grasping points, even though it might be rotational. So for example, one thing we did and why we use the nozzles for the upper stage, of course, one, because it's mostly commonly, you know, known target object, but secondly, because it's quite symmetric in its you know, in its look. As you can see, it's spherical, it's quite symmetric. So that kind of mimics something. If it's rotational, you kind of know roughly what you have to deal with when there are behaviors that are quite symmetric in itself. So when it comes to any rotational behavior, you still have to map the object first and determine where to grasp. And in the control side, the navigation, because it's all relative still in the 3-axis space. So in this case, the control would be more complicated because maybe it's not to do with controlling in only the lateral space of the 3-dimensional field, but you have to consider the other 3 rotational. So that's something I think you have to build into the control of it. So we sort of tried our best in terms of being able to demonstrate it in the hardware, but in the software we can do more demonstration of that. Maybe some of the talks in the afternoon would be able to show you some of those more unique, if you like, and more special cases. Yeah, but in the demo, we are in fact, unfortunately limited by what the hardware can do and the safety considerations. But the principle still applies, but you have to understand the space has to go through those mission stages that the industry is currently using. So we can't completely change that, because otherwise it wouldn't make it easy for our industrial partners to take on board what we developed. So you have to be quite respectful to those mission stages that is currently quite accepted by the sector, and see how you can plug their existing solution and replace them with ours to improve the performance. I think one of them is the orbital navigation. Yeah.
Thank you very much.
No problem. But if any other researchers will add to this point, I would just briefly pause just in case my colleagues from the other 2 sides want to add to my answer. As I said, we do have opportunity in the afternoon to elaborate on those scientific details. Yes, there's another hand from the Surrey side, just from the audience.
I'll try to be quick.
Kate.
My name's Kit Lee. I actually work for the MTC Catapult company. I've got a question here. How close would you think the effects of, for example, the booster attached to its own structure into an enlarged structure, what would the effects be? And I appreciate the torsional motion of it, but if it was elongated, for example, the nozzle attached to the rest of the structure, what would the potential problems be? And also, I was wondering whether the servicing gripper, would you take on board the benefits of being able to look at the current sensing on the arm itself and do the force feedback as well?
That's very good 2 questions. So I would take the first one to begin. So the first one, I think, relating to the scalability of our solution. Yeah, I think I see, Kate is nodding to me. So basically, just to confirm on the software side, it is scalable. So for the moment, the demo, as you're saying, obviously has been tuned so that it works with this particular size of the demo test bed and the particular scene in the in the scenario, but it is scalable. So through the research phase of our activity, we actually tested extensively different types of targets on the different lighting conditions, on the different dynamic situations. So hopefully some of my slides in the afternoon could fill in that gap to confirm that scalability. Because as you said, for example, when the target has a different mass associated with the grasping point, which will be the case, okay, then the arm and the gripper and the algorithm all has to be addressing that new type target. Again, this is all part of that inspection perception stage of the mission. So actually you would expect before you actually start controlling the arm, there is a phase of approaching which you will be doing that mapping, estimation, in terms of inertials, in terms of the actual surface condition. So the whole technique is actually is scalable. Okay, so that's to answer your.
One question:
Yeah.
Are you taking notice of, for example, the work that Astroscale is doing with their search and capture, for example, and watching the behaviours of this magnetic docking, for example? Are you watching that?
Yeah, so for example, there are commercial sort of solutions. Astroscale is one. For example, when they have this example you just said is what's regarded as a corporate target. So they have predefined mechatronics interfaces. So to be honest, there might be some trade secret in their current work in terms of visual navigation bit, which is understandable. So they haven't actually openly or detailedly announced what exactly behind their algorithm, but we believe a part of that is based on fiducial markers, which just so you know, we are using fiducial markers as a kind of benchmark solution to compare our solution with. So both for cooperative testing, because you only have fiducial markers for the corporate target, because you can't put a fiducial marker on a non-cooperative one. So we did use that as a reference to compare, and we actually do have publications on that. So that's something just to confirm. It's something we're comparing with, because we know the fiducial markers, you can call it a benchmark solution. We know how to do it. We know how to tune the parameters. But the reason why we say our solution is more versatile and scalable, because it just assumes your target is unknown. You have very limited knowledge of it, and you want to be able to adapt in real time. That's why in the demo, as you say, Sam was trying different spots, because that was all randomly generated behind the screens and computers. So there's no pre-programming, it's just randomly put in there, but it's still successfully doing it repeatedly. And you can see, when you change lighting condition, the algorithm will adjust the better spot to pick up that object, just to show, because it has to optimize all the energy. That's why you can see, I think hopefully you can appreciate that it will find the shortest one to go to save the energy, save the time. But your second question, sorry, I forgot your second question.
Force feedback.
Oh, yes, from the servicing.
From the servicing.
Exactly. So actually, a very good, so the short answer is yes, we do, because you can see from the second part of the demo with the security measure, the one that we are using as a 2D image fit to double checking how reliable the sensor is on board is actually, we're assuming is coming from a camera view on board the mother spacecraft of the servicing arm. Of course, this could be sitting also on the space station. So yes, it's definitely, we are looking into that fit. But at the moment, for the actual guidance for the navigation, for the grasping itself, we haven't used that as a dependency, because we want to remove that as a dependency of, for obvious reasons. What we want to argue or offer to our potential users for the technique is to say, if you have those visual feeds from your mother spacecraft or servicing satellite, it's just added value, because we can take that in to do the validation. So one of the things, for example, from our collaborating partner at Manchester, Claire's team, we work very closely with them, is to use that sort of extra sensing input for onboard or real-time verification. So this is all part of the algorithm. So it's not just the actual AI implementation and navigation as we traditionally do, but we're adding security element, we're adding runtime verification checkpoints, and this we call third-party inputs from the mission are all inputs we're using. So yeah, that's my extended answer of the yes.
Thank you.
No worries. But again, I'm going to pause just in case my other colleagues from the team want to add to any of my answers.
I think you did a good job there.
I guess that, oh.
No, I think you did a good job there.
So casting any hands from your side?
We have indeed, so.
Oh, Imperial, yes,
Yep.
I saw the notes now.
Yeah.
Hand over to your hands from the Imperial side.
Claire Dixon, University of Manchester. This is a question to the Warwick team. What other attacks did you consider?
So throughout the programme, what we've done is considered, as part of this and some other work we're doing with the European Space Agency, is to consider a range of different attacks. And what we do is we do something called threat modelling. And to do that, we consider a range of different scenarios, including who's going to conduct the attack. We're in interesting times at the moment, as Dan alluded to. There are many commercial organizations with interests in space as well as nations. And what we do is we look at who are the threat actors, who's going to try and compromise a system, how will they try to compromise the system? Do they need remote access or local access? Do they need access? Or Saurav showed the point cloud manipulation. So that could be in the AI manipulation. So it could be something that gets introduced in the supply chain, which we've seen problems of before, or it might be something that's done live at a time. It could be some proximal satellite that dumps some payload onto another piece of space equipment. So we looked at all of these different scenarios, and this afternoon I'll talk a little bit about how we developed a reference architecture to help us analyze these threats. But in terms of the demonstration, this was the main thing that we did with the active debris removal, because of the limitations of time. So what we did is we conducted an attack, explained how you might mitigate that attack using multimodal information, overcome that attack, and then show that resilience. But we've got them more theoretical. I think, Saurav, we didn't do any others in a practical sense, did we? Or did we do another one?
No, this is the only one. But we got another attack on the neural network as well.
So please.
Just wanted to add, we have another, we did some work on adversarial inputs in the neural network for the pose estimation. So we've got the poster for that and outside as well.
Okay, yes,
Yeah.
and that's the work that here at Imperial there is a poster. There's some work that was presented just last week in Big Sky in Montana on pose estimation. So there is that work as well. I should apologize to Anita, who did that work. Thank you, Claire. Any other questions from the audience here at Imperial before we go to Edinburgh? Okay, I think there's no more questions here, so I think we can go over to Edinburgh to see if there are any questions up there. No questions at Edinburgh. Do we have some from the internet?
I think there's some nodding heads from the room. So we have something online, perhaps.
Yep.
So can I rely on my colleague from the tech team to maybe read out anything from our virtual participants?
Can you hear me?
Yes, someone is talking. I don't know from where, but
from the tech team in Imperial, watching. We're talking for the online community here. So we have a question from Praveen Kumar. Within ADR, what do you feel would be the safest, most efficient and cost-effective way of actually capturing a debris object? I know various companies are trying to develop different methods, like using a harpoon some sort of funky net, robotic arms, magnetic plate capture, etc. Maybe it's too early to tell, but any thoughts from you at this stage on this subject would be very helpful. Thank you.
That's a very understandable question. I think we got asked very often about this. Of course, as a roboticist, as we appreciate completely that the different mechanisms that we can develop to engage, to retrieve, as I was briefly touching on in my presentation earlier, we choose the multiple degree of freedom robotic arm for this particular demo or ADR demo for various reasons. It doesn't necessarily mean this might be the most promising one in the immediate future, but there are a number of practical reasons we choose it rather than other mechanism, is because they offer such a great flexibility, degree of freedom that really allow us to test navigation, guidance, and control, which we know can be reused for other space mission scenarios. So that means this could be a very useful and relevant technology in the catalog for the space community. So they can use it for not just ADR, but for other corporate target scenario like servicing, manufacturing. And because it's such a comprehensive system in the sense that it involves sensing, guidance, navigation, control, and also extended from the standard sort of satellite system, as you would appreciate. Therefore, this is regarded as really, if I could call it, value for money. So you have the R&D developed not just have a singular use, let's say the net, like the fish net, maybe that would be a very unique platform for specific things. I'm sure it has its own advantages over robotic arm, but you have to, you probably would appreciate what we're doing here is comprehensive, is reusable, it has a much wider impact and benefit. I think very often, I sense people ask this type of questions is also because there's an underlying reason why people ask, is they probably understand there are such a wide range of situations in orbit when it comes to debris. Okay, they come in different sizes, they come in different configurations. They are also created due to different situations. Sometimes they're retired satellite, which is an integral, object, and sometimes they're pieces, which is after a incident. So because of that, it is very understandable. There are different more suitable robotic mechanism. If I leave the software aside for the moment, just look at the mechanism to engage physically, and I can appreciate that different robotic mechanism could provide different costs of your solution. So because of that, my personal view is we should keep all these different mechanisms available. We should develop all of them as in a catalog of solutions, like a shopping list of solutions to our sector. But we should also, I think due to the funding, limitation, prioritize the development among these possible solutions. Of course, robotic arm, in my personal view, should be prioritized because it's so versatile and more controllable, because the controllability in space is so important to stress, because a lot of generation of new space debris was due to the fact we lost control over those engagements, and therefore they created more debris rather than removing or reducing them. So this is my answer, not giving you a direct answer to say, oh, this is the one you have to go for the best. I'm just saying they all have their pros and cons. It'd be great if we have a shopping list of all of them, but in reality, we need to prioritize the development of the technology that probably at the present time, it gave us the best, value for money and benefits in a wider sense. But that's just my perspective. I'm just going to pause again if there are any of my colleagues from the team want to add to that answer. Okay. But I think we're happy to take any, probably one more. I'm just watching time. I think we have a few minutes left, but we probably have time for another, if any. I'm just looking at my tech team. If there's another question from the virtual.
Yeah, Yang, we have one here at Imperial got a question.
Yes.
Oh, yeah.
Can you hear me? Oh, great. Gregory Befanu, University of Warwick. Just a rather generic question in terms of the ADR demonstration. What kind of open challenges you foresee, both technical and scientific, still remaining open as part of this activity? And what's the potential future plans on addressing those? Thank you.
Sorry, I did not hear the question too well. Costin, could you paraphrase? Is the question about more generic?
Yang, he was asking about what are the open challenges that you think for ADR in the future, and what kind of approaches do you think there might be to address those challenges?
Sure. I think this is a very good slightly higher level question. So of course, ADR as a mission involve different stages. And it actually starts, just in case colleagues are unaware, it started with actually detection, tracking, and monitoring the space debris. So for instance, there are knowledge and technologies, even in the UK, are looking at some of the sensoring technologies or observatory technologies, either ground-based or orbit-based or space-based, to look at mapping the space debris to begin, which is understandable. We need to understand the evolution of the debris. We need to understand their behaviors, because I recall the first question from our audience here asked about, their orbital behaviors, because we need to have better understanding of their properties, their dynamic properties, their natures at that sort of monitoring stage. And then we move to, more in action stage of the actual space segment, which involve your servicing spacecraft, which involve the actual robotic element. So what we've been demonstrating, because this consortium really are roboticists, so we focus only on the robotic side. But if you look at the bigger picture, there are also other aspects of the whole mission that need to be looked at. There is energy issue. I mean, this is all part of the sustainability, the energy issue on the servicing setup, or even people talk about having infrastructures in orbit, like a gas station in orbit in the future that can top up fuel for your servicing spacecraft that can go out and do this cleaning up. So they are all parts, if you ask me, of the bigger picture, but also integral steps that need to be put in place if we are seeing any of these ADR missions to fly in a commercially sustainable way. I think we can already fly demonstration missions, meaning we fly something test, which we demonstrated on ground, or with real world data sets today. But if you want such a mission to be a commercial sustainable service, people would be willing to pay for, people would be willing to have a business for and create jobs around it. You really have to look at not just the robotic bit of it, but the rest of the, supporting the housekeeping bit, from the communication, power, the initial kind of mapping, cable track for the daybreak map, all that, they all have to be in place. But hopefully we contributed our bit, and we just need also the rest of the overall picture to come together. So again, I think that other people can also contribute from the team. If there's something to be added, just pause. That anything else? I think we are coming to the end of the slot we are giving, Carsten. We're coming to, I think we're right on time.
Thank you very much, Yang. Thank you. That was. Thank you very much to everyone for the questions as well. I think we have some questions maybe that were on the internet that we haven't managed to answer. But Yang, perhaps if Sam, yourself, and any of the other researchers involved can have a look at that over lunch, we'll try and answer those questions or follow up with email. But now, as Yang said, we move to the break. So there will be a 1 hour break. We'll be back at 1 o'clock. I do urge you, for those on the internet, to join us back at 1 o'clock, because here from Imperial, we're actually going to be controlling a robot up in Edinburgh. So that will be a live demonstration here, and we'll have some presentations afterwards. For those in Surrey, Edinburgh, and Imperial here, we'll now break for lunch and give the opportunity for those at the local sites to see the robots actually in action at each of the sites. So thank you very much, and we'll see you at 1 o'clock.